associated with this talk. I put it together in just a few days, so it's a bit rough and ready. And also it's mainly based on my own previous work, and at various stages you'll see that I've gone quite a way back in time. And so right at the outset, especially since these broadcasts are available for people around the world to see, I don't want you to get the impression that the field just stopped when I stopped working on my little bit of it. Things have actually moved on a bit since some of this work, and I'll try to mention that again when I get to that. Second apology, of course, is that although it's nice to be here in a mathematical institute, I'm not a mathematician. I'm in the theory group in the Department of Physics at Warwick, and actually I'm not even really a theoretical physicist. I should be mainly concentrating on the computational aspects of this. So I don't develop some of the theories that you'll see here. Other people do that. I just do some of the number crunching to get some answers out. So I'm very bogus indeed. Actually, if you look at my qualifications, you'll find I'm not even a physicist. My first degree and doctorate were in chemistry. And since I got an MA and a DPhil, you may even wonder whether I'm a scientist in the end, since the word science doesn't appear anywhere in there. So now I've completely destroyed my credibility. And yes, so things can't get any worse. Things can only improve, and hopefully, well, we'll see where they go. So several parts in this talk. I'll give a little bit of introduction to the models, and then we'll see where we go from there. So I do computer simulation to go along with some of these theories. And most of the stuff I'll be talking about today involves hard particle models of liquid crystals, that is hard ellipsoids of revolution, so typically with a long axis, and it's axially symmetric about that axis. So of length A, of width B, and various elongations, but because I'm concentrating on comparison with Onsager theory, I'm concentrating mainly on the upper end of this elongation range, which is where the Onsager theory is most accurate. And for good old spherocylinders, of course, length L, width D, and elongation, of course, really it's L plus D over D, but we normally just call it L over D. And again, fairly elongated particles here used in some of the simulations that I'll describe. Here's sort of one slide version of Onsager theory. So this is the free energy here in 3 dimensions, 3 spatial dimensions. So here, the figure 1 really represents the position and the orientation of these particles. Because I'm only considering axially symmetric ones, I'm just using a little unit vector here for the orientation. And then the free energy functional in the Onsager approximation is a combination of single particle terms, the first of which is recognizable as the entropy of mixing of different species. And of course, in Onsager's classic approach, when we've integrated over the positions, those different species represent different orientations of the molecules. So it's a classic sort of rho log rho kind of formula. And then also we can put in here the external single particle potential, which sort of plays 2 roles in this field. In one of them, it's a kind of a trick that you use to establish some of the basic formulae of density functional theory. There's some transformation going back and forth between functional derivatives with respect to the density and functional derivatives with respect to a spatially varying externally applied potential. But then the other aspect of it, of course, is that it can represent the container walls or some externally applied field and the way the system actually physically responds to that. Here's the pairwise term, and you can think of this as the first in a density expansion of the free energy, and this is the term that's sufficient to give us a phase transition. So it involves the density at 2 different points in space and for 2 different orientations, and it's an integral over both of those sets of quantities, and then there's a coupling term in between the 2, which is the Mayer F function, and that's defined by the pair potential in between the 2 molecules. And so this is a well-known function in liquid state theory. at the low density limit, the Mayer F function is equal to the direct correlation function. So for some purposes, you get functions rather like this, but with F replaced by C as the first term in a functional expansion of this free energy with respect to density. Well, in fact, it is the appropriate second functional derivative of F with respect to the density. So this sort of formula may look familiar from that side of things. But from the numerical computational point of view, the important thing about this is that if you make the Onsager approximation and stop the expansion here, then there are no adjustable parameters here. You feed in the interaction between the molecules, you get out a free energy which you may then minimize with respect to all possible variations of this rho here, and that's the answer. You know, you like it or lump it. The integrals are over all the spatial coordinates and all the orientations. In Onsager's theory, of course, the integrals over the positions are done straight away on the assumption of a homogeneous system, and you end up with this term here representing a pair-excluded volume for molecules of prescribed orientation. And that gives you something that you'd often call B2 of the two orientations, and then there's a lot of interesting sort of physical interpretation of that.
Cutting down the phase space to stop the molecules.
Not stopping them, no. This F function takes care of their intersection. So when the potential is very large here, this becomes 0, essentially. And then you get a -1 where the Mayer F function is. And where the potential is essentially 0, outside interaction range, then these two terms disappear and the F function becomes 0. And then the details depend on how it varies in between.
You're not conserving particles here explicitly.
I am. Now actually when we come to the practicalities of this, I'll add on a mu-n term, I'll subtract off a mu-n term, and then typically the way we minimize it is to allow the number of particles to vary and either specify mu or have mu as a Lagrange multiplier in the minimization process to keep n fixed. So I haven't gone into that, but yes, the grand potential is really what we should write down here in principle. And so you get an extra rho term inside this integral there. I missed out one or two other factors like the de Broglie wavelength because I just didn't think it was important to put those in. Just a formal volume term to make the dimensions here consistent, and I haven't bothered to put that in. So, Onsager theory, it kind of paved the way to modern density functional theories. Of course, because it's a density expansion, it's only valid for low densities, but it's not specifically restricted to smooth variations of rho. Rho can vary as you like, in principle. We could make that restriction and then that would naturally lead to a gradient expansion, but we're not going to do that. So this term here, the F12 term, is a non-local term, it's a real term, but of course it is bounded in range by the interaction range of the particles. Can be empirically extended to higher densities, and this was an early attempt by Friederike Schmidt to do that. 10 years ago now. Friederike, incidentally, is going to be visiting Cambridge, arriving late, I think early March. She's visiting Dan Frankel's group, and I'm hoping she'll come along to our workshop, the second workshop, but even if she doesn't, she'll be around. And she's a very smart German theoretical physicist. She took over the chair that Kurt Binder used to occupy in Mainz a few years ago. And then other people have also tried to extend it to higher densities. One of the things they try to do is to keep consistency with the Onsager limit at low densities, because of course that is asymptotically correct at low densities. Usually then when we apply Onsager, we simply take L over D tends to infinity. So we really do take this limit of infinitely long and infinitesimally thin particles with a constraint on the product of the two to get the units right, so nothing actually explodes, so it's not pathological. But that's not what we do. We actually compare Onsager theory with real molecules which have a finite thickness and a finite length. So for that, of course, we use the actual F function that corresponds to those models, so we actually calculate it. And
What
Well, there's no implicit restriction here that that rho should have any kind of that should vary on a length scale that's long compared with anything in particular. So rho can vary on a molecular length scale if you want it to. And the theory is equally valid, but it's only valid at low density by construction. That's what I meant.
The molecule have a volume that's proportional to LD squared.
Yes.
So why is L squared D squared constant?
Well, that's the
makes them bigger.
that's the that's the result of Onsager. That's to do with the way that the excluded volume scales with the molecular dimensions. So it's not a volume, but it's the way that the orientationally averaged excluded volume scales. So it's convenient to take that out. So you'll find that in the Onsager theory, in that limit, the phase transition happens at a value of density which is given by rho L squared D equals a certain number, a universal number. In fact, there are two coexisting densities, isotropic and nematic. And then you can actually take this limit. And you'll see I actually represent some of my results in these units as well.
So where does the excluded volume come in because you said that you weren't putting a constraint on the overlap of the molecule?
Not constraining them, no, but when you do this integral over the spatial coordinates, then effectively in the spatial integration, the only contributing values of the integrand are when this f function is non-zero.
But the V12 is defined for, that doesn't blow up as something.
Well, V12 may blow up, but because it appears in this Boltzmann factor here, this function f is more or less on a scale of 0 to -1. V here can go to infinity if you like, and then this term will disappear. And that more or less defines the volume, or the range, over which you get non-vanishing contributions to this integral, when the two particles are within that range.
But it isn't infinite when two particles overlap?
No, f isn't. V may be, and that's perfectly right. Yeah.
V is not infinite when two particles overlap?
V can be infinite when two particles overlap, yes. So for high particles it is. And in that region, this term will be infinite, the exponential of minus this term will be 0, and f will be -1. So you can think for high particles, f is almost like an indicator function of whether things overlap or not. It takes a value of 0, -1. And for softer interactions, which we do sometimes use in our simulations, then it varies a little more smoothly between 0 and -1. And of course, the other thing about it is that in all of that, it depends on the orientations as well. And that's where the Onsager approach to how the excluded volume depends on those relative orientations. That's how all the physics of that comes in. Okay, now what we did a few years ago, not the only ones, as I say, not even the first, was to look at the way this varies in a homogeneous system, spatially inhomogeneous system, which varies in, let's say, one dimension. That doesn't mean we're dealing with a one-dimensional system, just that the density is only allowed to vary in one dimension, and it's assumed to be constant, homogeneous, translationally invariant in the other two directions. So that enables us to deal with the situation of a planar interface, for example, or anchoring against a planar wall. And so typically, just number crunching away, we would parameterize a single particle density, which we do by tabulating it on a regular grid in Z space, in the Z coordinate. And also at each point in Z, we would expand it in spherical harmonics. So the quantities that we can vary are these coefficients here. You don't have to expand to a very high order in spherical harmonics. This expansion plays the same role as Onsager's trial function did in his theory. His trial function was a very nice, simple one-parameter trial function. We're just doing an expansion up to some order, typically fourth order. And actually we expand a logarithm of this function, which means that we can allow quite steep variations in angle, but it's always, rho is always guaranteed to be positive. So and that's good, because we don't want the density to be negative anyway. And then having done that, the other ingredient is this f function, and because we're only considering variations in the z coordinate, we can pre-compute some of the spatial integrals. If we did all of them, we'd be back at the original Onsager theory, but what we want to do is to pre-compute the transverse integrals x and y, in which there's no variation of the density, so we simply do this part of the integration first, and we get something that kind of has the units of an excluded area. That is, an excluded area for two particles that are held a given distance z12 apart in the z direction. So we just move them all over the place, and then this quantity, apart from the negative, well, yes, with the negative sign there, that represents the kind of area in which they overlap. And then we can expand that. In fact, we expand it in symmetrized rotational invariance, basically. So we're basically expanding it in a set of spherical harmonics of both of the two participating orientations referred to the z-axis, the direction along which we're allowing spatial variations. So there's a certain amount of manipulation of indices in this, but basically we get a coefficient expansion of this, which we take up to quite high order in L, because of course these are hard particles and the things vary quite dramatically with orientation, so we want to go up to quite a high order, and we do a little bit of empirical checking, L max equals 8 or 10 or 6 or whatever, just to make sure that things look as though they're converging. I'm afraid that's about as rigorous as we get when it comes to testing for convergence. And grid spacing, we haven't done a huge amount of investigation on this, but we're using quite a fine grid spacing, something that's about 1/100th of a molecular length. We have to use something that's fairly small, because remember, the particles we're dealing with are quite narrow, so typically this distance here is maybe only 1/10th of a molecular diameter, so it's not quite as fantastic as it looks. And then do conjugate gradient, like I said before. So an early attempt to play with this was to look at anchoring. What we would do is to imagine a system between two walls, a wall on this side which we would use to fix the orientation of the director at a large distance from the interface of interest. And so along with this wall we'd have some kind of orienting field. For the wall we'd use a planar surface which acts on the centres of the particles, be they ellipsoids or spherocylinders or whatever. And that means that at any kind of reasonable density, such a wall would naturally induce homeotropic anchoring. That is, the way the ellipsoids naturally pack with each other to maximize the free volume, the most efficient way of doing that is to have them normal to the interface. So this isn't a neutral wall in any sense. This kind of wall actually induces homeotropic anchoring all by itself. But then we could change that if we wanted to by adding some extra orienting fields to either make it a tilted anchoring or to try and counteract the effect of the homeotropic anchoring, although we haven't tried to do that. It is also possible to have a wall that excludes the entire particle, and just a flat wall that doesn't allow it to penetrate at all, and as you might guess, that favours planar anchoring. Other people have studied that. I think Dijkstra and company have studied that by simulation and also, I think, by theory. But this is the wall that we've used, together with an orienting field, and then there's a region of unperturbed liquid crystal, and then at the other side there's the interface of interest, and I'm going to talk about two things here. One of them is another solid wall with the homeotropic anchoring, and we just wanted to make some measurements, see if we could measure the anchoring coefficient for that, see if everything worked out all right. And then the second one is somewhat more interesting, the equilibrium isotropic nematic interface, so the free isotropic nematic interface at equilibrium, although in the presence of a wall at some distance. So the first one, fairly easy to understand. Here's the orienting field region. I've coloured it in green here. The region over which these wiggly black lines appear, that's the region in which the molecule centres can move around, and the black, that's our simulation results.
So what do you mean by orienting field?
Well, it'll be a field that couples to each individual molecular unit vector, and it'll be an energy that depends on the angle of that. So it will strongly favour one particular direction. And the idea is that the details of that don't matter. It's just a way of fixing the director at large distance. So it does behave in an interesting way here, but we're not actually interested in measuring it. It's just a way of prescribing
So
the
this
director.
is modelling the interaction of the wall with the...
This is adding a bit to the wall, but actually this isn't the wall we're interested in. We're only using this as a way of specifying like a boundary condition in a crude numerical sort of way. So it's almost like specifying Dirichlet condition. What I'm plotting here is the angle of the director in a plane, the z-axis along here, and then some other chosen axis, let's say the x-axis. That's the direction in which the director is allowed to vary. And so we fix its direction, and then we measure the angle of the director all the way across the slab of liquid crystal here till we get to the other wall. And this wall is of the kind I just described a moment ago. It's a solid wall just acting on the centers of the liquid crystal molecules with no extra field at all. So as I said, we expect that to favor homeotropic anchoring. And you can see it does, because whatever angle we force the director to be at on this side of the slab, it's trying to make that angle 0 at this side of the slab. Of course, it doesn't succeed, and the extent to which it doesn't succeed is a measure of the anchoring strength. And by doing a fit to these curves here, which is more or less a linear fit on this wall here, we can get an extrapolation length, lambda, which gives you the ratio of the anchoring strength to the bend elastic constant. And this fit basically is a 2-parameter fit. It starts to curve a little bit out here because over this side you're starting to see bend turning into splay as you get across to the other side here, and the angle has turned to almost 90 degrees, and the splay elastic constant is slightly less than the bend elastic constant.
Is that a fit parameter?
I think it was, but we have actually also measured the elastic constants for this kind of thing. That is possible by other methods. Firstly, it is possible to measure the anchoring coefficient by this kind of crude simulation. We can do a fit, but on the other graph here, what's nice is that if you just feed those same parameters into the Onsager theory with nothing else to adjust whatsoever, it produces these blue curves here, which are not a bad representation of the true simulation results, including a little bit of the structure that you get near the wall here. And there is some structure near the wall. It's not just a uniform fluid near the wall. The density does actually go up and down a little bit near this wall, and the Onsager theory gets some of that. I haven't shown the density, but as well as that density variation, there's also a little bit of order parameter variation and a little bit of director variation as well. And it's not perfect, but it's a reasonable fit there.
Are those blue curves coming in horizontal at the far wall?
That's an interesting question. Not quite. And yeah, I mean, I think I know what you're asking. I wouldn't like to extrapolate the gradient and the value exactly at that point, because I think these coefficients we're talking about are really mesoscopic coefficients. I don't think they're microscopic coefficients. So the behavior at contact, it might be interesting to measure it, but I don't know if I could interpret it very well.
Do you need to define director in introducing?
Yeah, so for all of this in the simulation results, I have to define in slabs, narrow bins, I have to define an order tensor and then diagonalize it and then get the director out of that. And that's averaged over the x and y direction. So there's a fair number of molecules involved in the simulations. In the Onsager theory, it's similar. You've just got the single particle density, and out of that you define the director in the usual way by constructing the second rank order tensor and diagonalizing it.
Of course, the definition of the director at the level of simulations is somehow tricky.
Yeah.
Because there is no good notion for the director. Do you somehow fit your molecular definition to what Onsager says?
Not really, no. We do it in the usual way in simulation. That is, we construct the averaged second rank order tensor, possibly over quite a long simulation run, and it's averaged also over quite a lot of molecules, and we do that on a fine grid in Z. So we have a spatially varying second rank order tensor, and then diagonalize it and measure the order parameter in the director.
Of course, you must limit somehow the sphere of containing some number of molecules over which you average to get the director.
Well, no, it's in a slab, so it's you know, the full X and Y system size, but then rather narrow in Z. And of course, yeah, there's a little bit of discussion about how wide that should be, and there's a trade-off of resolution and accuracy. Don't forget, for this system here, well, I say don't forget, I haven't really said, but this is in the nematic phase for a 15:1 ellipsoid, so the order parameter is quite high. I'm not talking about anything that's close to a phase transition. Now, all of those questions that you're thinking about will be much more important when we look at the nematic isotropic surface, when really there's a lot of doubt, I think.
Oh, sorry, so it's planar at the right-hand wall, the alignment?
No, it's homeotropic again, for the same reasons I said before, that the surface is only acting on the centre of the molecule. So you can think of the ellipsoids as half penetrating into the wall. So all it does is it's an excluded volume, or exclusion, which acts on the centre of the molecule.
But if it was a real wall and a real molecule, then it would want to be plane.
Yes, yes, it's a choice.
Right.
You know, we decided to do this. If you want a physical representation, I try to pretend it's a little bit like having a wall which is coated with a polymer brush or something like that, into which the molecules can penetrate, something like that. But of course, it's just a crude toy model, really. It's, yeah.
So what is the simulation have you actually done here?
Well, they're Monte Carlo simulations in between two walls.
How many sort of?
A few thousand, typically. Yeah. For this sort of system, you don't need a huge system.
And you said you'd done some, it was somehow one-dimensional, so I haven't quite understood how that.
The Onsager theory is one-dimensional in the sense that the density is allowed to vary with respect to Z, but is assumed constant in X and Y. In the simulations, it's a fully three-dimensional box, fully three-dimensional Monte Carlo. The X and Y dimensions are just chosen large enough that the periodic boundary conditions are satisfactory, and it doesn't have to be huge for that to hold. Nematic isotropic interface was really the target for the next study, and this I think is quite interesting, and it's a bit more challenging, or at least it was then. This is still about 12 years ago, so I think we could do better now, and it might be worth going back and doing some of this stuff again. So let me try and explain what's going on here. This again shows simulation and Onsager theory. In the simulations, the density is chosen to be in the isotropic nematic coexistence region. So it's at a density which will phase separate into the two phases. The system is again between two planar walls, and typically at one of the walls there's a small region where we apply this orienting field again, but for the moment forget about that, just think of this as being two walls. And one of the walls, well, both of the walls favour this homeotropic alignment, and that means that you'll see, close enough to the phase transition, you'll see wetting by the nematic phase. So you'll see a wetting film form on one of the walls. Now, this study actually wasn't specifically to look at wetting or, if the walls are close enough, capillary condensation. But the language is, you can think of as being similar. You vary the chemical potential around the phase transition value. If it's just below the chemical potential for the phase transition, you expect to see this wetting film form. And for this system here, you can just get it closer and closer to the phase transition, and the wetting film will just get thicker and thicker. And as I say, we didn't actually look in detail as to whether there was a transition between a thick film and a thin film, and between a film and the capillary condensed state. We simply used these parameters to look at a film on each wall and made sure that the region of isotropic phase in the middle of the box was wide enough that the two walls didn't seem to affect each other very much.
Excuse me for that. These are dumb questions. When you say you do a Monte Carlo simulation, you're doing what exactly? You're doing molecular dynamics with... I mean, no, at least when you say theory there, is that Is that a simulation? I mean, because that's a big problem, this Onsager thing. That's also a computation.
It is.
Theory is a computation.
Yes, it is. It's probably best to think of it like that. So the last point first. The theory is again Onsager theory.
It is Onsager.
Yes, it's Onsager theory in this geometry with the external potential provided by the walls, with the density tabulated on a grid, on a very fine grid. So a single particle density with those coefficients that I mentioned at each grid point. So representing the single particle density as a function of orientation at every point in Z on the grid, expanding it in spherical harmonics. And so there's a set of coefficients that specifies that single particle density. And then that goes into the Onsager formula for the free energy, which involves doing that numerical integral over all the spatial and orientational coordinates. So we do that using orthogonality and so on. And then we minimize that numerically. So that's what I mean by theory.
So how do you enforce the isotropic state in molecular dynamics in Monte Carlo on one of the ends? Okay,
so turning to the simulations, the simulation is done in that same box with the walls, and the total density of the system is in the coexistence region. Remember, it's a first order phase transition. So if you're in this range of densities, which for long thin particles is a reasonably wide target. I remember Onsager theory predicts a strongly first order phase transition. You can see here the two densities involved in both the theory and the simulation. So you have here two walls, a large slab geometry. You just do the Monte Carlo and the system will phase separate into two pneumatic films adsorbed onto the wall and an isotropic region in the middle.
So what I remember, because I have much less experience, of course, with simulations, that be fluctuating regions. So when I run a molecular dynamic simulation of this kind, for example, I will not have an isotropic phase in the middle of, say, between two pneumatics. There will be just a mass of bubbles, which fluctuate all the time.
No, if you run for long enough, you will get, there will be fluctuations, yes, and that's the whole point. The simulation will average out those fluctuations. For a system like this, where the transition is reasonably strong, you'll get quite good phase separation with planar interfaces like this in between the two phases. And you can see that happening. Yeah.
I believe that it would be correct if you force pneumatic on the ends, but the bulk energy would prefer isotropic state, and indeed inside you average to isotropic, but once you're in that intermediate region where you have both pneumatic and isotropic states, I don't see a reason why on the average inside you'll get any kind of isotropic state.
No, that's not true. For any first order phase transition, well, that's not worked out very well, you have some kind of order parameter which has a probability distribution, and it'll typically have two peaks in it, like that.
Yeah.
And that's including all the fluctuations and everything in a box of finite size, even without any walls. And if you have a small box, then this distribution comes about because the system goes back and forth between the two.
Yeah.
But if you have a large box, it occurs because the system is phase separated into two macroscopically large regions. And it does that for the same reason as it does in real life, and that is to minimize the surface tension. So what you'll find is that the configuration with the smallest surface area, the interfacial area, will dominate. Now, of course, that doesn't mean there won't be other configurations with lots of bubbles or droplets around, but because they have a larger surface area, their free energy will be larger and the probability of occurrence will be much smaller. So you see this region down here really almost always corresponds to this sort of slab geometry where you have one phase in the middle and two planar interfaces.
Okay.
If you have periodic boundary conditions, of course, an alternative is for it to form a spherical droplet. And we do rely on metastability and also the relative dimensions of the box play a role here. For the boxes we're using, the transverse dimensions are not enormous, and this kind of configuration is the lowest free energy.
I see. Actually, your comment about spherical geometry is good, because we have a spherical geometry, in fact, and our bubble It's probably a sphere just tries to kind of run around.
I'm
Because
sure it would,
actually
yes.
it doesn't change the surface energy.
Yeah, it could do that without changing the surface energy.
Yeah.
With us, it's a combination of kind of the boundary conditions, which are periodic, and the dimensions. But it's quite a common geometry. And actually, you'll find now, more recent work on measuring surface tensions of fluid systems, they look at this kind of geometry and they run for long enough that you can actually see variations of the relative amounts of the two phases occurring over the course of the simulation. If they get the chemical potential exactly right, so the two phases are at exactly the same chemical potential, the same free energy, then the conversion of this into this with conservation of the total surface area here costs 0 free energy. And this kind of plot here turns out to have rather a large region in the middle corresponding to fluctuations of the positions of these interfaces back and forth. But we don't see that in our case because we have these walls here and everything essentially gets pinned.
To get this state that it's isotropic in the middle, do you have to be, presumably then the isotropic phase has to be the global minimizer system. Otherwise it's all just go pneumatic, right?
Yes, so it's, you know, you're very, very close to the phase transition, but if you like, you're just below it.
Yeah.
If you're sort of at it or just above it, then it would capillary condense and fill out the whole thing.
There's lots of different densities there in terms of this phase separation, this phase, isn't there? Because so you're going to be close to the density where the pneumatic phase loses stability.
All you have to do to be is so the overall density is anywhere in the middle of the coexistence region. So it's just like in any first order phase transition, and the lever rule will apply, and it will split into two phases in proportion to where you are on the overall. It's like in the rho T phase diagram of liquid vapor.
Okay, so that's your blue line moving. Is that you changing the density?
Yes, basically, or if you like, the chemical potential.
Yeah.
So either of these.
Okay.
So a couple of things I should say then.
Excuse me.
Yeah.
Your simulations are at constant chemical potential or at constant density?
No, they're all at constant density, actually, yes. So it's a lot easier that way.
The temperature.
These are 8 thermal
Hard particle system, so there's no, the temperature doesn't play a role. So yes, right at the beginning of this series of questions, you're asking about how I did the Monte Carlo. So you move the particles around randomly, and if they overlap, you reject the move. If they don't overlap.
Your Onsager theory, so
Actually, if you look closely, you'll see the temperature divided all of the energies out. So you could just take it as unity if you wanted to. You'll find, if you liked, you could write the Onsager theory entirely in terms of F over kT and temperature disappearing.
So this model doesn't predict a phase transformation at a particular temperature?
Not at a particular temperature, no. So hard particle systems show phase transitions as you change the density, or if you like, the pressure, or the chemical potential. But the temperature itself isn't relevant. And that's true in colloidal suspensions as well. In colloidal suspensions of rods and plates, the temperature is not particularly relevant except insofar as it affects the solvent properties a little bit.
So hard particle systems are not good for modeling liquid crystals?
They're very good for modeling colloidal liquid crystals. They're good for modeling colloidal liquid crystals. And also, it's been well known for years in liquid state physics that hard particle systems are always a good reference system for modeling other systems which may depend on the temperature. So you can add on attractive forces as a perturbation afterwards. I don't want to get too far into that because it's off the topic, but they're worth studying, and you can think of them as being simple models of liquid crystals, but it's true they don't. You know, if you empirically put in something where the dimensions of the hard particle effectively are temperature dependent, so by turning the temperature you basically change the shape of the molecule a little bit to represent the effects of softness, then that's a kind of crude way of getting the temperature effect. Okay.
And it's just a hyperbolic tangent on the order parameter, right? I mean, it looks like...
It's not far off, yeah. Yeah, all of these are not far off. If you really look closely, especially for things that we get very good statistics on, like the order parameter here, you can see it's not perfect and symmetrical. Hyperbolic tangent, it's not a perfect fit, but it's not too bad.
Sorry, Michael. Could you just spare just a few more details on the interaction potential that you are using in this case?
Well, these are hard ellipsoids. So
So it is the true volume of hard ellipsoid?
so it's the overlap criterion for hard ellipsoids. So there are at least two different equivalent mathematical ways of formulating that. And it's the same one used in both the simulation and in the Onsager. Happy to discuss how I do it afterwards if you like, but it's fairly well known. Now the blue curves here, we've got quite a lot of them because it's easy to just change the parameters in the Onsager theory. So I changed this parameter here, or equivalently the total number, and of course you can make this film thicker and thicker and thicker as you like. And after you move away from the very thin film here, once you get out into this sort of regime, it doesn't really make much difference. You're just simply making the film thicker, but the interface is pretty much the same. This quantity here is the order parameter, the pneumatic order parameter, the P2 of cos theta order parameter. Anyway, you can see how it varies. This is pretty close to it is the value in the bulk, pretty much. The two black fuzzy lines here, they're fuzzy because those are statistical error bars that we have to measure in the simulation to give you an idea of the statistical error due to the fluctuations and the limited run length. So those were estimated as reliably as we possibly could. We did two separate simulations, one on a relatively thin film and one on a rather thicker film. Didn't do quite so many runs as we could do for the Onsager theory. You can see, and we didn't actually hit exactly corresponding states, so you'll just have to judge by interpolating where the corresponding blue line would be, but it's pretty good. Down here is the number density, and again I've used this scaling, rho a squared b. Remember the length is a and the width is b, and if you did take the limit, a goes to infinity and b goes to 0, this reduced number would mean something in the Onsager sense. Actually, usually for spherocylinders, but here there's a similar sort of thing. As you make it larger and larger and larger in length, this will tend to some universal number for the pneumatic phase, which is this horizontal line up here, and for the isotropic phase, which is this line down here. So these are the two phases in coexistence. This is the interface between them, and the different lines correspond to a thicker and thicker film. You'll see that doesn't match at all well with the simulation results, but that's quite normal. Onsager theory overestimates the coexistence densities for actual real hard particles. It's an approximation, it's not an exact theory. Notice there's a shifted scale here of density. Here's 4, 5, 6, 7, so it's not an enormous error, but it's a well-known error, and of course our inhomogeneous calculations don't suddenly make that discrepancy go away, it's still there. So you can see the shapes are very similar, and apart from that sort of shift, it's a pretty good representation. Also you can see here the layering near the wall, which I mentioned earlier. As I said, we tried angling the director at the wall using an applied field, and that's interesting because then, just like in the anchoring case that I showed you before, it will tend to turn as you go across the film from one side to the other if the natural alignment at the isotropic pneumatic interface doesn't match the one at the wall. And you can see from the way this is going, the natural angle at the isotropic pneumatic interface is 90 degrees. It's trying to get to 90 degrees. And I'll show you a bit more evidence for that, quantitative evidence, in a minute. But the point is, you're getting here director rotation as you go from one side to the other. Here is where it was fixed at more or less 60 degrees at the wall. By the time you get across to the other side of the film, this is for our thick film and this is for our thin film, you can see it's getting pretty much all the way, nearly all the way, towards 90 degrees. If it's 30 degrees at the wall, it doesn't make it anywhere near as far, but it's still trying to get in that direction. If it's fixed at 0 degrees at the wall, so it's just sticking out from the wall, then it doesn't actually do much. So there doesn't seem to be any symmetry breaking or anything. It just heads out into the pneumatic, and then the order eventually peters out as it reaches the isotropic pneumatic interface. So you don't see any direct rotation in that case. For the 90-degree in-plane orientation at the wall, there's no reason for it to change, and it simply stays the way it is all the way out to the isotropic pneumatic interface. Here's some snapshots of what it looks like. So these are, as I said, 15:1 ellipsoids, so they're quite spindly. Here you'll see the normal arrangement at the wall. This is only the snapshot of the middle part of the box. The box actually is much longer than this in both directions, but I've just picked out the region where the interface is. You can see on the right hand side here it's all rather disordered and entangled, and the interface is around about here. And this is the arrangement where the thing started out in the plane of the wall, and again this is where the interface is. Here is where it was tilted, and here is where it was tilted the other way at 30 degrees and 60 degrees. Again, I don't think you learn very much from these snapshots, but you can get an idea that there's a lot of fluctuation going on there, and we average over all of that in the simulation. One of the things I'm very interested in is the calculation of the surface tension of that interface, and obviously the director variation of that surface tension is pretty much related to the anchoring energy of the liquid crystal at the pneumatic isotropic interface. In computer simulation, we measure that by calculating the pressure tensor. This formula has been around for a long time. Close to the interface, the normal component of the pressure tensor and the transverse components of the pressure tensor are not equal to each other, and the difference between the two of them gives rise to surface tension. And in fact, if you do the difference and integrate over the entire interface, then you get the surface tension. Far from the interface, on either side, the pressure tensor becomes isotropic again, so these two terms cancel out. And actually, for a fluid-fluid interface like this, it's easy to see that the normal component of the pressure tensor, the one that's along the axis going normal to the interface, that's independent of position anyway, so it's just a constant. That's the mechanical pressure. If it were not constant, then the fluid would rearrange itself to make it constant. So that component of the pressure tensor is just fixed. So it's only the transverse component that varies with z as you go through the interface. Of course, the x and the y components are degenerate, so they're equal to each other. Now, interestingly, or not, depends if you're one of the handful of people who likes this kind of stuff, there isn't a unique definition of this wretched pressure tensor. Not for a non-local model. For a local model, you can create something like that. But for real life, at least the way we've defined it so far, this has some non-uniqueness associated with it. It's only really the gradient of the pressure tensor which plays a physical role in systems. Microscopically, this isn't something that necessarily needs to worry people who are dealing with macroscopic scales, but at the molecular scale, there is some ambiguity. None of the ambiguities affect the value of this number, gamma, at the end. They all integrate out when you do the integral. They vanish identically. But they do affect the profile of the pressure tensor as you go through the interface. So they affect the way you describe the interface. So we're interested in just looking at that. This was quite tough. I mean, here are the error bars again, and you can see I'm really stretching your credibility now because it's very noisy. I was really pleased when my student managed to get these results out and they actually matched the theory. It's one of those cases where it's reassuring to have a theory that agrees with the simulation results. It gives you more confidence in the simulation results. So let me show you what you've got here. This is the order parameter again. I've scaled it so it goes from 0 to 1. Don't worry about the values here. But the idea here is just so you know roughly where the interface is. And then this is the difference between those pressure tensor components that I mentioned, and this is for the two interesting cases of alignment, normal to the surface and in the plane of the surface, the director. And you can see there's pretty good agreement between the two, and the second thing to notice is these are very different from each other. The surface tension profile depends dramatically on which of these two alignments you've got. This is the integral of that quantity, going from left to right, starting at 0 on one side, going through the interface, and then eventually, of course, it plateaus out on the other side here. And the height from 0 to this point here, that is the surface tension. So the first thing to notice is that this height here is bigger than that height there by, I don't know, about 50% or so. So that tells us that the surface tension of the planar-oriented director is lower, significantly lower, than for normal alignment. So that backs up what I was saying before about the anchoring at the isotropic pneumatic interface being planar anchoring, not homeotropic anchoring. So we actually have a number there. These numbers are quite small, as I say, they're quite difficult to estimate, you can see from the error bars. Where does that tension come from? Well, here's where we start talking about the profiles. In this case, most of the tension comes from this peak here on the pneumatic side of the interface, and then on the outside, on the isotropic side, there's a little bit of a sort of a rebound here, what you might call a compressive region. When you integrate the whole lot, you get something positive. And the story is the other way around if the director is oriented normal to the interface. So that's sort of interesting, not sure if it means anything. Clearly, it will mean something if you've got a droplet with a curved interface and there's a director structure inside the droplet, and the anchor or the direction of the director near the surface varies, is forced to vary away from the locally minimum free energy. So we've had a look at that. I wanted to say a bit more about this ambiguity here, although probably at this stage we don't want to dwell too much on the equations. I'll just mention a couple of the conventions for defining this transverse component of the stress. What it amounts to is looking at the forces that act between particles at different positions in space, looking at a contribution to the stress tensor that arises between particle 1 and particle 2, and then deciding how to distribute that in the fluid. One of the choices is to just put it at the end of the line between the 2 points in the fluid. And actually by symmetry what you end up doing is you divide it in two and put it at both ends. So it's like localizing the stress at the positions of the 2 particles. There's another definition which has become more common, and that is to spread it out in the z direction in between the 2 particles evenly. So essentially you take that number and you slice it up into little bits and distribute it in the bins all the way between the 2 particles. One of them is due to Hiroshima and the other one is due to Irving and Kirkwood. And as I say, the two of them give the same values for the surface tension, but they give slightly different looking profiles. And what was nice for us is that we could calculate the results in both of these conventions from the Onsager theory. All you need to do is just go into the Onsager theory and just deconstruct it a little bit more and realize that it contains an approximation for the pair density. The pair density is what formally goes in here, and the only difference between the two is whether you integrate over an intermediate coordinate between the particles or not. So it's possible to calculate these profiles from the Onsager theory much more accurately than you can calculate them in simulation. And here are the results. And these are the two conventions in 2 different colours. You'll see they give very similar shapes to the curves for the normal alignment and for the in-plane alignment. And the differences between the 2 conventions are fairly minor by comparison with the size of the effects that you're dealing with. And also you can see this is the stress curve and then this is the integral of it. You can see what I said is true, that once you integrated it, although the running integral depends on where you are and which convention you're in, as you go across the interface, by the time you reach the other side, the 2 curves will come together again and you end up with the same value of the surface tension. Now this is a sort of interesting mathematical point, although I'm not sure how many people at this program will be interested in it. The whole question of these profiles and where the surface of tension is located. In a sense, the surface of tension is given by the first moment of this curve here. And you can think of it mechanically as being the place where the tension is said to act in the surface. And there's been debate for decades on whether this surface of tension can be defined properly and how much it's displaced from the Gibbs dividing surface, which is similarly defined by basically the first moment of the density profile. The difference between those 2 points, those 2 positions in the interface, is called the Tolman length. And as I say, there's a lot of debate as to whether the Tolman length is non-zero, whether it's positive, whether it's negative. And the reason for that is that it plays a big role in the surface, the free energy that happens when you curve a surface like this. So when you go from the planar surface to a curved surface, the value of the Tolman length dictates whether there's a positive or negative extra contribution to the free energy that comes when you do that. And it's a very fiddly question. It's still not completely resolved. Those people who are interested in it, I can point you to a recent review by George Jackson. Just came out this last month, I think, in Soft Matter. We've measured where this surface of tension is for our two cases here, for the two conventions, and you can see, as you might guess from the different profiles here, for the case of normal alignment, it's on one side of the surface, and for the case of the in-plane alignment, it's on the other side of the surface. So our prediction for the Tolman length is that it depends what direction the director is in, whether you get a positive number or a negative number. Now I should say that if you go to longer spherocylinders, we've gone from 20 to 50, these numbers, which are in units of the length, L, I should have made that clear, these units get smaller. So it's entirely possible, we haven't checked it yet, but it's entirely possible that this Tolman length will vanish as you make the particles longer and longer and longer. That might be something worth looking at. But perhaps that's enough of that. The last few minutes, I'll just show you some pictures. So, having done this in one dimension, we've extended this Onsager treatment to 2 dimensions. And as I say, this is not the current state of the art. I think people, Paul van der Schoot, for example, in the Netherlands, has been looking at this whole Onsager treatment for looking at liquid crystal tactoids, pneumatic tactoids and things like that. So it certainly is possible to extend it to 3 dimensions, and I'd be quite interested in cranking up our programs and looking at some interesting 3-dimensional problems to see what structures of director and defects and surfaces you get out. But I'll just show you some work that we've done in 2 dimensions. This is with a cylindrical nanoparticle, which is coming out of the board at you. Again, with homeotropic anchoring, no special reason, but it's the one that's easiest to implement. In a pneumatic where the director is oriented to point straight up and down on the screen here. And you can see the classic sort of defects running down the sides of the cylinder into the liquid crystal here. And so you can vary the size of the cylindrical nanoparticle. So the solvent here is again these long thin ellipsoids, but it could equally well be some other shape, it's not really critical. And as you get closer to the phase transition, these 2 points here are at exactly the same state point, same value of chemical potential, but one of them is on the pneumatic branch and the other is on the isotropic branch. The isotropic branch, you can see the ordering that's induced by the spherocylinder here. It's uniform all the way around, and here is the structure in the pneumatic with the defects along the side here. They're a little bit bigger, of course, as you get close to the phase transition. The liquid crystal is less well ordered. The order parameters dropped a little bit. And then we can try bringing in a cylinder towards a wall, and this is in the pneumatic phase. On the top is just the density, number density again. On the bottom is the order parameter variation on a scale here. Again, you can see the densities, these lower values of order, as it gets closer and closer to the wall. But more interestingly is what happens when you're just on the isotropic side of the phase transition again, because there, out here in the isotropic, there's no order. There's liquid crystal ordering around the nanoparticle. There's liquid crystal ordering near the wall. As they get closer and closer, you get a bridge forming between the two, and you get something that's a little bit like capillary condensation. And we can measure the grand potential as a function of the separation of the cylinder and the wall, and indeed you can get a switch over from one regime into the other, and depending on the chemical potential you can either see a gradual growth of the pneumatic ordering, or you can see a jump as this bridge forms, and then you can actually pull it apart, see a little bit of hysteresis, and then at some point see the bridge break and going back to an isotropic going back to an isotropic in between the 2 particles, the wall and the cylinder. So I won't go through that too much because of time. And you can see again we can do 2 cylinders approaching one another from different angles. See the way the defect structure distorts a little bit as they get closer. You see this well-known effect. Remember, this is still in 2 dimensions, but it's well-known something similar happens in 3 dimensions. And to an extent, some of this can be perhaps better described with a Q-tensor theory or Landau-Lejeune type theory, but it was quite nice just to see it coming out of the Onsager theory directly, and we can look at the structures here on the molecular scale. I'll skip all this because of time, but obviously you can do structured surfaces as well. And here are various people who worked on this. And yeah, and Bob Evans will be here in March. He'd be a good person to talk to about it. René Van Rooyen may be coming to join us at our second workshop. He's just got an invite to fill a gap, so I'm hoping that he'll come and tell you a bit more about it if you want to hear. Good. I'll stop.
Questions? What are pneumatic tactoids?
Sorry, pneumatic tactoids. My apologies, yes. So, droplets, but typically not spherical because of the competition between the surface tension and the elastic behaviour inside. So it's a pity Paul can't come. He was invited to come on our Friday BLCS sponsored day, but he had to pull out. So it would have been interesting to hear him describe what he was doing there.
The tactoids also have these pointy ends on them, or is that
Yes.
part of the definition of tactoid?
Oh, well, this I don't know. I think of them as just being droplets of interesting shape.
Nick Abbott and De Pablo had a publication recently where the pictures looked a lot like yours of colloidal particles in pneumatic. And they had some size dependence, I remember, I think.
Mhm.
That was,
Yes.
Did you look at size effects in here?
A little bit. All of the pictures I just skipped by you, they're all in Onsager theory. So I showed a little bit of size dependence on the cylinder size. When we did simulations, we actually did some simulations of both cylindrical particles but also spherical particles, and there we did look at the size dependence, but those are quite old now, and I think the more recent work you can really crank up the computer power and look at size dependence. It is quite interesting. We managed to see, again, homeotropic anchoring. We managed to see situations in which you both have a Saturn ring defect around a colloidal particle sphere and one where you have a satellite defect. And that was surprising because we didn't think the satellite defect would ever be stable, because we reckoned that the predictions were for it had to be much bigger. But in fact we could see that it was stable. You never know in simulation if you run long enough, maybe it will become unstable. But we certainly could see a particle which was big enough to apparently have a satellite defect at one pole, which was stable for as long as we cared to leave it there, and then if we'd make the sphere a little bit smaller, then it would become unstable and would migrate around and up to the equator and become a Saturn ring. But that's as much as we did. That's probably not really state of the art. So De Pablo, who is also coming, isn't he, to our workshop, I think his abstract says it tells us a bit more about that kind of thing.
At the risk of repetition, could you just say a few words about how you get this Onsager model with this exponential? Maybe you could go back to the
How we get... Let's, oops.
introduction.
Yeah. Control panel. Just grappling with Windows after having had a break. This one.
There we go.
Okay. Different people have different ways of getting this, but this is the ideal gas contribution to the free energy. So if you switched off all interactions between particles, then basic statistical mechanics would give you this. Just trying to think how you do get it.
I think it was just a form of F12, I suppose.
Yeah, this is part of the so-called Mayer F expansion of the free energy. So it is part of a rigorous expansion in powers of the density involving pairwise interactions. We're assuming pairwise forces, pairwise potentials in here. And you just get pair terms and then triplet terms and then fourth order terms and so on. Which in principle, if you continue to infinity, will give you an exact result. In most problems, that expansion does not converge. So In simple liquids, it doesn't converge. That is, you can never see any discontinuities in the free energy. You can never see any divergences in the free energy to give you a phase transition. But in the case of highly non-spherical particles, you can show that it does converge, in the sense that the integrated second and third and fourth virial coefficient terms scale in a well-defined way with the L over D ratio, such that they can be shown to get smaller and smaller and smaller as you go to higher order. And that's partly where that L squared D scaling comes in. I could dig out a review in which you get this, I think, or Bob could explain when he comes. He probably will be intending to explain it as part of his talk when he comes in March. I'm not the world expert, I have to say.
So if this is a term that pops out of an expansion, what does it look like before you start expanding? What is the base, what is the home?
Yes, good question. Yeah, good question. Can't think at the moment. I think my recollection is that you write down the free energy of a statistical mechanical system in the way we usually do. That is an integration over all of the particle coordinates, let's say, so the multiple integral of the Boltzmann factor, and include in that an external potential term. And then formally, I think what you do is a functional derivative with respect to that external potential, which is a very well-defined thing, which we can all relate to. And then there's a trick, which converts that, I think, into functional derivatives with respect to the single particle density. So I think it's a bit like a Legendre transformation or something like that. But I'm not the person to say, especially if I'm still being broadcast. Oh good, yeah, Lech is better qualified. I mean, I can just imagine Bob in his office, you know, seeing this and chuckling to himself and thinking, what's that idiot Mike going on about now?
Sorry.
But I can dig out the review.
It's a generalization of the so-called virial expansion, which is known for simple liquids.
Yeah.
Just by saying that constant density is replaced by density distribution. And by this, and you start doing this expansion using grand canonical ensemble, where you introduce external potential, and as you said, by formal Legendre transformation from external one particle potential to the density, they are coupled variables, so to speak.
There, excellent, good. So I remembered some of the words and put some of them together in the right order.
Then you go via graph expansion. It's quite involved, so I have some notes if you are interested in.
It would be good to see.
I pointed Ibrahim towards a paper, a recent paper, which takes this first step in a different way. I don't know if you had a chance to look at it. No. Okay. So again, I think it's Matthias Schmidt, who is another of these, really clever density functional guys. I think he thought about this and this slightly tricky indirect way of introducing it and turning from a functional derivatives in terms of an external potential into derivatives with respect to the single particle density. And I think he thought, well, this, there must be a better way of doing it. And he did devise such a way, which is based on a variational principle of some kind. But I was hoping you, being a real mathematician, would explain it to me at some point.
I looked at it already, but not in enough details to
Okay.
see how much it differs from what I thought
Right.
originally, so I didn't.
Well, I tell you what, I will upload it onto the forum,
Okay.
and then nobody need feel obliged
Force people.
by having it appear in their email box. But if anybody wants, I'll put it there under the little Onsager thing that I put up there earlier, and anybody who wants can have a look at it and see if it makes sense. At the least, it will have some pointers in it to the traditional way of doing it, which I find so difficult to explain. But as Lex said, easier to think, okay, if you just make these homogeneous functions just constants, then you can recognize here now the virial expansion of the equation of state. So this is the second virial coefficient of non-ideal gases, basically. And then the next term will be the third virial coefficient, and so on. And that gave an easy interpretation to Onsager's theory, because he could talk about it as the free energy of a non-ideal gas mixture, where the different components of the mixture simply differ from each other by being pointing in different directions. But as long as you're happy with that, which you are, of course, then this is the entropy of mixing term that any undergraduate chemist or physicist would write down based on the mole fractions of the composition of that mixture of many, many components. And then this would be a double sum over the pairs of components of the partial densities of each of the components with an appropriate Mayer F function representing the interactions between them. So actually, if you ignore the variation with position and orientation, it is a very basic formula from undergraduate thermodynamics.
Can I ask a question, a different question? So do you see long-range pneumatic water in your simulations for
Oh, yeah.
years? So it's always long-range. Is it because it's hard particles? Because as soon as when I try to simulate, not hard particles, there will be no long-range water, but this temperature, of course.
Yeah.
And then it destroys. Basically, this is the same as like zero temperature, more or less, all the time.
Not zero temperature, no. No, I wouldn't say it's like zero temperature, because then you get a crystal. You're used to thinking of crystals being at zero temperature.
Sure, but this temperature scaled out, yes.
The temperature scales out, yeah. But so what's the problem? Certainly, if the phase diagrams for these have been very well established for a long time. So of course, there's a minimum elongation below which you don't get a liquid crystal. But above that elongation for these ellipsoids and also for the spherocylinders, you do get pneumatic phases and in some cases smectics. And so on.
My question, maybe I didn't express it clearly. So if I take a very large system and only take hard particles, will it have long-range order? So will the orientation of my pneumatic phase be the same throughout the entire system, or will it have domains?
I see. Well, of course, I see your point. Yeah, in principle, even for these hard particles, if you take a large enough system, you'll get the same kinds of disorder and the same kinds of defects occurring naturally in them. So yeah, you'll get the same limitation on long-range order that you get in real liquid crystals. And that's not really dictated by the temperature, but it is dictated by the fact that you have density fluctuations, you're bound to get disclination defects and so on. We never do simulations on that scale. They're outside the range that we can tackle, as you can work out by working out what kind of range they occur on in real life. So we're dealing with like 1 million particles at the most, I would say, and it's like 100 by 100 by 100, and you need to look at a larger system in real life to see the decay of order with defects.
A very naive question. When you do surface tension,
Yep.
one is used to think of surface tension as energy difference per unit area. Why don't you compute that?
No, you're quite right. It's the free energy per unit area.
Yeah, sure.
So these methods are a way of translating that into something that's easier to measure in a simulation through pair forces.
Easier to simply sum up the difference of energy in the transition region?
Well, no, it's not possible, because that would only give you the energetic part. It wouldn't give you the entropic part. So certainly, for a solid, you could get a good estimate that way. You can get for crystalline surfaces, you can get an estimate because the energy part will dominate. But for this, no, you have to include all the fluctuations, all the entropy contributions, and so on. So you need something a bit more. It's not even clear that this mechanical route is absolutely right for fluids. There's been some doubt cast on it. For planar interfaces, I think it is correct. For non-planar interfaces, it's very difficult to define this particular route correctly or unambiguously. And that's what some of this debate about the Tolman length has been about over years and years and years. But the formula I gave do basically come down to free energy per unit area. And the idea is you imagine doing a small change in the area and calculating the free energy, and then the statistical mechanics gives you these formulas, so you don't actually have to do that change.
Okay. Well, thank you very much.
Well,
Thank you.
thank you very much.